Good afternoon, everyone. Welcome and thank you all for attending today's Nanometrology webinar, part of a series sponsored by the National Nanotechnology Initiative. I'm Anil Patri from the Food and Drug Administration's National Center for Toxicological Research, and it's a privilege to host this meeting on behalf of the NNI, along with my co-host, Dr. Elizabeth Mansfield from the National Institute of Standards and Technology. We recently celebrated the 20th anniversary of the NNI. The US government R&D initiative brought significant resources that enabled the development of new tools, methods, and techniques to evaluate nanoscale materials and devices. It enabled significant advances in various fields, resulting in novel applications to benefit society. Metrology at nanoscale is quite challenging and exciting. The intent of this series is to showcase advances with the measurements and tools and resources available at the national labs and in academia to provide opportunities for collaborations. The webinar series started in spring of this year, covering the historical aspects, applications in food, agriculture, environment, and medical products and electronics. Matt, can you go to the next slide, please? Maybe the next slide as well. Yeah, so this is the metrology webinar series that I'm talking about that started in spring, that covered a wide range of topics listed here. By the way, all of these webinars are available for viewing at the NNI website. You can go to nano.gov website and watch these videos. We showcase the nanometrology for continuous and automated manufacturing and emerging field to make materials at nanoscale a month ago, with the inline and at-line measurements, with the challenges of these systems that bring and pose to scientists. Next slide, please. One of the many challenges is to analyze large data sets resulting from nanometrology at high resolution and during continuous and automated manufacturing. Today's webinar describes the types of measurements and computational analysis challenges when dealing with the large data sets from high resolution measurements. By the way, this meeting will also be recorded and posted later online, so you can visit the nano.gov site if you have to miss part of the presentation. Also, please use the Q&A chat box to ask questions. We will cover these questions at the end of the panel. We are happy to have an excellent panel today, and I would like to welcome the presenters. Dr. Colin Offus is an associate professor in the Department of Material Science and Engineering and a center fellow at the Precourt Institute for Energy at Stanford University. He moved there recently after serving as a staff scientist at the National Center for Electron Microscopy, Molecular Foundry at Lawrence Berkeley National Labs. Welcome, Colin. Dr. Subramaniam Sankaranarayanan is a group leader of the Theory and Modeling Group at the Center for Nanoscale Materials at Argonne National Lab, with a joint appointment as a professor of mechanical and industrial engineering at the University of Illinois at Chicago. Welcome, Subramanian. And finally, Dr. Kamal Chaudhary, he's a staff fellow in the Thermodynamics and Kinetics Group, Material Science and Engineering Division, Materials Measurement Laboratory at the National Institute of Standards and Technology. Welcome, all of you. I will now turn it over to Dr. Colin Offus to start his presentation. Thank you.
All right, thank you very much for the very kind introduction, Nano. I'm just going to share my screen. Can you guys see it okay?
Yep, looks good, thank you.
All right, so I will get right into it then. So I'm going to be talking about a technology known as 4D STEM and its applications to a couple different various areas of nanometrology, and in particular, the gigantic amounts of data that are generated and some of the solutions that we've come up with to deal with those giant data sets. So as a brief introduction to transmission electron microscopy and scanning TEM, why do we do it? It's because it has unmatched spatial resolution. So if you want to look at individual atoms, TEM is almost always the technique of choice here. And so if I just zoom in here, this is showing 3 different generations of transmission electron microscope that were installed at the National Center for Electron Microscopy, part of the Molecular Foundry user facility at Lawrence Berkeley Lab. And so these individual atoms, you can see these are columns of atoms, the same sample, silicon nitride, and each white dot in the upper right is a single column of silicon or nitrogen atoms here. So you can see that we're working down at the atomic scale when we use these tools. We were able to develop them with several different technologies, including aberration correction, better detectors, and computational imaging. And especially these last 2 are what I'm going to be talking about today and the type of measurements that they enable. So I also like to show pictures of what the TEMs actually look like in case you aren't familiar with these. These are fairly large machines. They used to be about 3 stories tall. Now they essentially fill a room, and we operate them with computer consoles in the room next door typically, so that we don't disturb the environment of the sample while making our measurements. Okay, so what about scanning transmission electron microscopy? It is an immensely flexible technique. We can configure the atomic column for imaging. You can see here the green lines focusing down on the small red sample, and then we have various detectors to measure different scattered or unscattered electrons. And with aberration correction, we can make our probes below the size of an individual atom. We can also operate in diffraction mode, where we measure the diffraction pattern generated by the sample in the far field, and these measurements can be modified by phase plates or amplitude plates. And of course, spectroscopy and spectrometry. This is allowing us to measure things like X-rays generated by the electron beam, or the amount of energy lost by individual electrons for chemistry and bonding information. And then finally, all of these methods can be extended to 3 dimensions by tilting the sample. So we really call STEM a synchrotron in a microscope, to quote McBrown. So I want to now introduce 4D STEM. So 4D STEM is one of those diffraction techniques I mentioned before. We take our converged electron probe, we scan through the sample, and a traditional or conventional measurement, we'd have a single pixel, this annular dark field detector measuring the scattered electrons, and that's all we would measure at each probe position. But now we have very, very fast pixelated electron detectors, and we can record a full image of the diffraction pattern at each probe position, move to the next probe position, and repeat. And so that gives this technique its name of 4D STEM. It's a 4-dimensional data set, a 2-dimensional image recorded at each of a probe position over a 2-dimensional grid. So why is this challenging? Well, it's the huge amount of data generated. This is one of our early experimental data sets, but each one of these diffraction patterns is actually 40 by 40 positions averaged. If I zoom out to 7 by 7 positions average, this gives you a better feel for the amount of data we're generating. In this case, this experiment was about 420 gigabytes. It took 3 minutes to record. This year, we can now record a terabyte of diffraction data in 6 seconds. And so this is the biggest challenge with working with these data sets. So why would we actually want to collect all this data? Well, at atomic resolution, this is what you would get conventional imaging for a couple layers of boron nitride. And this is the 4D STEM tychography technique. Much better resolution, much better signal to noise. But from a metrology standpoint, this sketch shows why we want to do 4D STEM. We record diffraction patterns over the functional length scale of our material, and then we can perform many different experimental measurements. We can measure parameters like strain, the degree of crystallinity, classify the structures, or the orientation of crystals, as well as the conventional imaging channels. So 4D STEM can improve resolution and signal to noise, and maybe even more importantly, we can characterize the structure and property of our materials over their functional length scales. And this is because the step size of the probe is decoupled from the resolution that we get from our measurements. Okay, so let me show a couple toy models here. If you have a crystalline sample, you can see that each diffraction pattern is essentially acting as a fingerprint of the local structure and orientation. We can also probe disordered materials. On this toy model, on the right-hand side, I randomly displace all of the atoms. As our probe scans from the ordered region into the disordered region, our 2-dimensional diffraction pattern is replaced by these so-called characteristic amorphous halos. This is the structure factor of the material. It's also a fingerprint for the atomic arrangement, but in this case, it shows us there's no translational symmetry in this material. So this is an experimental data set recorded at the Molecular Foundry at Berkeley Lab. This sample started out life as single crystal gadolinium titanate. They ion irradiated it, the sample from Los Alamos, and then they annealed it to simulate aging. So you regrow from the crystalline amorphous front into the amorphous region here, the disordered region, but you also nucleate many randomly oriented polycrystalline grains. And since you've seen the toy models I showed before, you can see that our experimental data fingerprints the different regions here, whether we're in single crystal, polycrystal, the sort of mixed amorphous and polycrystalline areas, or when we reach the surface of the material, the fully amorphized area that's so disordered and so defected that there is no local crystalline order. So the tableau shows all of these different regions here. So how do we analyze this data? Well, my group has created a software called Pi4D-STEM. This is an open source toolkit that can perform many of these different experimental analyses that I mentioned. Here's a non-exhaustive list here. And I also wanted to mention that last year we received an R&D 100 award. And this is in part because of how useful it is to both the academic community and to industry as well, especially the detector manufacturers here. So that same sample I showed you before, here's just an overview of the different measurement channels here. We're measuring ordering, the orientation, the amount of strain, and the local chemical structure here. And this manuscript is in preparation. Okay, so for the rest of my talk, I want to show a couple different metrology examples of 4D STEM here. And at the very end, I'll have a semiconductor style one here. But first, I want to show soft matter. So this is conventional TEM of a block copolymer. And you can see that the authors here have produced a phase diagram. You can see the black and the white regions. These are the two different polymers that are included in the structure. And the vertical axis is the temperature that they were processed at. So we can understand the morphology here, but you don't know what the structure of the white or the black regions are. If you do a technique called atomic force microscopy, you can measure the surface topology of these materials. And then what authors do is from these topologies, they sort of imagine what the local mesostructure of the material is like here. And this is just comparing two different polymers, one with low and one with high molecular weight. So you can measure things like phase separation and some morphological information, but we have no information about crystallinity, orientation, ordering, or packing. So what we want to do with 4D STEM is transform these sketches into structure maps. So here's an example of a small molecule organic crystal. Here's the diffraction pattern. If I boost the contrast, you can see diffraction spots, and they correspond to the pi-pi stacking of this material here. And so if we measure the positions of all of those diffraction spots, we can then use software, in this case Pi4D STEM, to reconstruct the morphology of the crystal. So below is the raw experimental diffraction patterns, above is the reconstructed morphology. And so the left-hand side shows this T1 molecule, and the right-hand side shows the T1 with this DIO additive. And you go from these large, continuously turning grains to these very sharp overlapping grain boundaries. So the morphology is completely different here. And note the length scale. We're scanning over a micron or over 1,000 nanometers field of view here. If you were doing atomic resolution imaging, you couldn't really get much data because of how beam sensitive these samples are, but you'd have to stitch together thousands of these images to cover these length scales. And so this is what 4D STEM allows us to do, to overcome the sort of field of view restrictions while still picking up atomic scale information. So again, just to emphasize it for the T1 and the T1 plus DIO, this is what you get with conventional STEM imaging, and this is what we get with 4D STEM. So we replace those virtual images with these rich morphological maps of the local structure. So let me show another example. Here is a battery electrolyte. This is a pretty standard EC-DEC liquid electrolyte. And in this case, we were interested in characterizing it at -30 centigrade. I'm from Canada, and we want to make sure that our electric cars continue to work throughout the winter in Canada. And so what we wanted to do was characterize these electrolyte materials at this given temperature. So here's an overview image, and then a zoomed in overview, and then a white box there showing the region we did the 4D STEM scan of. And so here's a quick sketch I made of what we assume the microstructure is. And I just wanted to quickly show the experimental data below. And you can once again see that each of these diffraction patterns is fingerprinting the local amount of order and disorder in this material. But we can go a little bit further here. We can take this tableau and use simple machine learning methods and then classify different structural regions. So in this case, we ended up with 3 different structural classes, and panel E is showing the radially integrated diffraction pattern from each of them. And so you can see that there's very, very different structural characteristics, diffraction characteristics here. Panel F shows the sort of layout of these structures. But now what we want to do is figure out what these different classes are, the different regions of this material. So the spiky crystalline signals are very easy. These are dead lithium salts that have precipitated out. And so they are not liquid anymore. They're solid components that don't participate in the cycling of the battery anymore. And based on the diffraction vectors here, the lattice spacing, the atomic spacing of this material, we're pretty sure it's lithium PF6 here in this case. The gray and the dark gray regions are significantly more interesting to me. So if we do the radial integrals here, we see that these structures are very, very similar to each other, but this is on an absolute scale here. So this is our first clue as to what the different materials are. Blue is significantly lower intensity than red. Therefore, it must be much lower density here. And so we interpret this as the red region being the more dense amorphous or so-called viscous liquid phase, whereas the blue areas here are the true liquid electrolyte. And so we did a lot of molecular dynamics modeling to try and figure out where these scattering features come from here. And we landed on PF6 ions, whether they're densely packed, forming short-range ordering networks, or whether they're diffusely packed here. And so this model is definitely not the final word, but it's a pretty good hypothesis for how these different regions are formed. They phase segregate into regions of high ionic density and low ionic density, and thereby form this amorphous or viscous liquid phase and the true liquid phase. And the amorphous one is the one with the local amount, a high amount of short-range ordering here. So let me show another toy model here. These atoms I put closer together on the left and further apart on the right. And so this shows one of the most common applications of 4D STEM, measuring strain or deformation in materials, or if we calibrate it, the lattice constant here. So because this is a far-field diffraction measurement, it's in reciprocal space. So if our atoms are closer together, our spots are further apart, and vice versa. So all we need to do is measure the spot spacing, and we can infer the local strain or deformation or lattice constant of our material. So here's an example, battery cathode particles that were made in collaboration with Will Chu's group over at Stanford. Here's the 4D STEM measurement on quite thick primary particles here, showing all the detected diffraction spots and the lattice vectors below. And then with calibration, we're able to transform these into lattice constant maps. So the upper right panel is the C-axis, the center right panel is the A-axis, and the lower right-hand panel is the shear strain, so the diagonal 45-degree amount of deformation. So we were able to take these exact same samples up to the synchrotron and do X-ray spectroscopic picography, and we did this for fully lithiated, partially delithiated, and fully delithiated battery particles here. And then we use software code to align these channels together. So at each composition here, we now have a measurement or feature space where we know the local lithium concentration and the lattice constants. And so we were able to then use machine learning to derive the constitutive law in this case. So this is a chemomechanical law, meaning how does the local mechanical response depend on the local chemistry here? It's not terribly exciting. This is essentially a Vergard's law output here, but it does show the sort of promise of going in completely blind and then using these correlative multimodal approaches here to learn constitutive governing laws of materials such as these. So another example I want to show is in situ mechanical testing of high entropy alloys. And so these are the cobalt chromium nickel based high entropy alloys. And they're interesting because they have the highest known fracture toughness of any metallic alloy. And so there's been a whole raft of very interesting studies, essentially concluding that this high amount of fracture toughness is due to twinning on many, many different length scales here. So they have large scale macroscopic twins and very, very small atomic scale nano twins. So what do we want to do in these materials? We wanted to study to understand why they have superior mechanical toughness. And so to do this, we did a 5D STEM experiment. This is a sketch of the experiment that was carried out in collaboration with Annie Miner's group at Berkeley Lab, showing our push-to-pull mechanical tester. And then we go through an energy filter and do energy filtered 4D STEM on our K3 and continuum system here, and we get a diffraction pattern. And each one of these diffraction spots is actually stamped with one of the patterned apertures that my group makes to improve the precision of these measurements. So we're able to find and classify each of the Bragg peaks But more than that, we were able to pick up the signature, the diffraction signature of the matrix parts of the sample, stacking faults, and twins here. So we don't need to image at atomic resolution, but we're still able to pick up atomic scale defects, in this case, stacking faults and twins. So from a single individual 4D stem measurement, we get the conventional hat-half stem, just sort of showing a rough optical thickness of the material, but we also get the defect images showing twins and stacking faults, and the strain by measuring the very precise spacing between these spots here. So what we did is repeated this many, many, many times. So unloaded, here's the strain map of this, or sorry, the stacking fault and twin density of the sample, and then under load, and then unloaded, and then after 1,000 cycles where we load and unload the material. And the below row, we're comparing the high entropy alloy to pure nickel. And so in the first couple loading cycles, you don't see much difference. When you load it, you inject stacking bolts. When you unload it, the stacking bolts relax. But after thousands of cycles, the stacking bolts remain here. And so this is our proposed mechanism, the so-called rejuvenation mechanism here, where the medium entropy alloy has a property called short range order. And then as you load and unload over thousands of cycles, you destroy the short range ordering. This allows stacking faults to survive in the material, and they're at the front of the crack here. And you can see that they slow further motion of the crack. And so they act as barriers to diffusion of these defects here, whereas the pure nickel has no such short range order and therefore no such mechanism to prevent long-term deformation. Okay, so the last examples I want to show are, I mentioned fingerprinting both the local structure and orientation. And so this is what that looks like. Here's a paper from Edgar Rauch showing a correlation of the diffraction pattern with many simulated diffraction patterns at many different orientations. And you could do this with multiple crystal structures. In this case, a paper from Brunetti showing lithiated and delithiated iron phosphate here. So you get both a phase and an orientation map. And so what we wanted to do was add these capabilities to our open source toolkit. And so I'll just very quickly show what that looks like. You can load any CIF file, any crystal structure, or pull it directly from the materials project. And then you can do some scattering calculations here to generate diffraction patterns. And Pi40STEM can actually do the thin film kinematical, but also thick film dynamical diffraction as well. And we can do this over many, many, many different orientations and then do template matching against the experimental data. So here is a twisted nanowire sample from Mary Scott's group at UC Berkeley. The conventional image shows you the morphology of the nanowire, but not much else. And of course, we have a full diffraction pattern at each probe position. And so we're able, with some calibration here, to measure all of the patterns of these spots. And so this tutorial, by the way, is online at the web URL shown in the lower right, tinyurl.com/pi40stem, along with many other open source tutorials here. So here's what it actually looks like running in a Jupyter notebook. You first load your vacuum probe, you load your data, you do a bit of hyperparameter tuning to find all the diffracted spots. And then for each one of these probe positions, you compare against your simulated library and you look for the best match, the second best match, etc. And then you can generate the result, which is the in-plane and out-of-plane orientation in this case. So this is a simple model system. I want to show a more complicated example here. This is a functional ferroelectric hafnium zirconium oxide film. And this was done in collaboration with Elaine Diebold at Albany and Tokyo Electron Limited. And so here's the conventional image of the material. It's got a silicon substrate, a conductive titanium nitride electrode, and then the functional ferroelectric HZO layer, and then another conductive titanium nitride electrode. So the problem with these materials is they can form many, many different crystal structures. So here's just a couple of the possible ones, but the only one we care about is this ferroelectric non-centrosymmetric structure. And so what our software does is it matches all the diffraction patterns for all of these phases, compares it, and then generates an output phase map. And so here's the result. And you can see it's actually quite mixed. We have a mix of monoclinic, orthorhombic, and tetragonal phases here. And so we actually probably need to repeat this study with some tilting because telling these phases apart is incredibly subtle. We actually probably have to move to 3-dimensional diffraction to be able to nail them down with 100% certainty. So I think that's the end of my time. So I will just quickly thank my many collaborators and turn it over to our next speaker.
All right, thank you so much, Colin, and thanks to all the organizers for arranging this webinar. I'm Subramanian Shankar Narayanan, Group Leader of the Theory and Modeling at the Center for Nanoscale Materials, and I'll be talking about our project on developing a digital twin for spatiotemporal experiments on behalf of all the team members. And this is a collaborative effort between Argonne as well as the various nano centers at Oak Ridge and LBL. All right, so the first question is, why do we need a digital twin? So the DOE scientific user facilities, including the nanoscale research centers, are home to a variety of world-class spatiotemporally resolved characterization modalities. There are also the theory groups that engage in simulations across a variety of different spatiotemporal scales. And every year, there are several thousand users, a significant fraction of whom are interested in performing spatiotemporally resolved measurements to explore structural evolution and dynamics, energy and mass transport across material interfaces in a variety of different energy applications. And given the large number of users and the competition for instrument times is quite intense. Each user can only perform a small number of experiments, and the experimental time is costly and scarce. To address this challenge, we are developing a physically accurate, flexible, and efficient digital twin for in silico spatiotemporally resolved experiments. So we want to bring the laboratory environment virtually to users before the actual experiments are actually performed. So our vision is to develop a virtual platform to enable in silico spatiotemporally resolved experiments to probe structure and dynamical evolution of material interfaces across disparate spatiotemporal scales. Our digital twin framework takes advantage of the fact that many experimental facilities at the scientific user facilities characterize either time-dependent atomic positions and or time-dependent structure factors. The readouts can be predicted from dynamical simulations if the underlying models are physically accurate on time and length scales comparable to the ones being probed in the experiments. Due to experimental spatiotemporal resolution limits, those observables must be reconstructed from coarsened and incomplete real or reciprocal space information, necessitating advanced techniques such as phase reconstruction algorithms, which are informed typically by atomistic methods. So in this context, the AI, machine learning tools, and powerful workflows can provide a good solution to the so-called inverse problem of obtaining atomistic positions from experimental observables by augmenting the incomplete experimental data with atomistic simulations of the energy landscape. So furthermore, this AI/ML assisted multi-fidelity scale bridging also allows users to perform dynamical simulations on a reconstructed or inverted user-defined sample and exhaustively explore experimental controls and expected readouts in a virtual environment. So the success of the digital twin platform hinges on the seamless information extraction from experiments that serves as input to physically accurate yet efficient dynamical models running on high-performance computing and exascale machines. And the digital twin allows the users to exhaustively explore various experimental controls and obtain readouts. A small subset that displays the most interesting physics or chemistry or phenomena can then be explored in actual experiments. And these experiments can be iteratively used as training data for model improvement to close the loop. And so that is the idea. And in this, we build on many of the complementary AI/ML tools and workflows that are developed by staff scientists across various user facilities to successfully realize this digital twin platform. So our project consists of three interconnected components or thrusts. The first is to make accurate predictions by bridging the spatiotemporal gap that exists between the various disparate simulation scales. We aim to do that by leveraging the advances in AI, ML, and high-performance computing resources. The second is to solve the inverse problem. So we want to achieve better interpretation of multimodal data sets, overcome the spatiotemporal resolution limits in various characterization modalities, and retrieve real space information from reciprocal space. And now this information could be both used to validate and iteratively improve the model predictions in our Trust One. The third aim is to develop smart workflows that allow for seamless information exchange between the various simulation engines, AI, ML algorithms, and the experimental and synthetic data sets. So let me give an example from our work on what a digital twin would enable us to do. This is an example of a coherent diffraction imaging, which is a lensless technique to obtain a full 3D information on how lattice strain develops in a nanoparticle. And so it's an ultra-fast imaging technique, can be used in a time-resolved fashion to understand how lattice strain evolves in nanoparticles. So in a digital environment, we can take a core shell nanoparticle of gold aluminum in this particular case, around 100 nanometer in diameter, and we subject it to a laser heating with various fluences and use molecular dynamic simulations to track the evolution and response of this nanoparticle as it is being heated. So we can post-process the trajectories to extract the diffraction pattern and obtain reciprocal space information or the response of this particle as it is being heated. What we notice here is that as the particle is being heated, the lattice mismatch between gold and aluminum leads to a shock wave that actually propagates through the sample. And this shock wave leads to interesting differences in the simulated diffraction pattern. In that, we essentially see that it is not just the peak position change, which is typical of what will happen if there is a single component particle, which kind of breathes when it is heated. In addition, when there is a core shell nanoparticle, what we see is that there is also a peak width change. And so once we notice the conditions under which this happens, one can then go about doing the experiments and realize those. And then here we have the advantage that we have the real space information as well. So one could actually quickly understand what is the underlying origin of the observation that we have in the reciprocal space when we are doing these experiments. So this is an example, but illustrates how powerful the digital twin can be in both accelerating scientific discovery as well as improving user experience. As we saw in the previous example, the fidelity of the model is actually quite important. And so let me talk a bit about what we are doing in the context of multi-fidelity scale bridging using AI ML. So for those who are not theorists, there are a variety of different scales. We are using a technique called as molecular dynamic simulation, where we are solving Newton's equation of motion, and it gives information about how systems evolve in time. There are various flavors of molecular dynamics, from the highly accurate but computationally expensive ab initio molecular dynamic simulations, which are restricted in the time scale and length scales that they can access. At a slightly higher length scale, we have the classical molecular dynamic simulations where you approximate the interactions between the atoms. So now you can access longer time scales and larger length scales. And then at the other end of the spectrum, you have what are known as the coarse-grained molecular dynamics simulations, which allows you to now probe mesoscopic phenomena such as grain growth and so on. So each one of these techniques is very powerful, but there is a catch that as you go from the ab initio to the coarse grain scales, you are gaining in efficiency, but that gain in efficiency comes at the cost of accuracy. So given that, the force field that describes the interaction between the atoms or the beads in the case of a coarse grain model The challenge is how do we actually optimize the parameters for any given model? And so this is a challenge of high dimensional parameter optimization. And here what we have done is inspired by the success of reinforcement learning in AlphaGo. We have used this Monte Carlo tree search algorithm, but more importantly, adapted it to operate not just on a discrete space, which is the case in board games, but apply it to a continuous action space, which is typical of the problems that we encounter in most material science problems. So Monte Carlo tree search utilizes playouts to select the best possible action from the current state represented by the root node or leaf. So here playouts refer to random actions from the model that allow it to learn by interacting with the environment. So the larger the number of playouts, the better the model estimate of the reward, and more promising is the model action selection. So notably, the MCTS performs this search in a tree structure, continuously growing either those leaves of the tree that result in maximum reward, also known as exploitation, or those that have not been adequately sampled, which is the exploration. So it is important to understand that when the action space is discrete, a parent leaf will exhibit finite possible child leaves, all or some of which can be assessed for their prominence. But when the action space is continuous, which is what we see here, the number of possible child leaves are infinite, irrespective of the depth of the parent leaf, making the use of MCTS or Monte Carlo tree set seemingly impossible in continuous action space. So a typical Monte Carlo tree search involves node selection, expansion, and back propagation. So here, the different coloring of the nodes indicates the depth of the MCTS tree. The algorithm balances between exploration, which is the lateral expansion of the nodes, and exploitation, which is the depth expansion of the nodes. And what we see here is the objective value of the MCTS, what a typical parameter landscape looks like. So it is a simplistic representation of a two parameter space problem. So the in-plane axis correspond to two independent parameters. The out of plane corresponds to the objective values, which is defined typically as the weighted sum of errors of the model predicted energies. In this case, the training data that we use are clusters with the target being the DFT reference energies. And this objective is what is minimized by this MCTS algorithm. So each sphere represents candidates of different model parameters within the MCTS1, where the differences in the vertical positions indicate differences in their objective values. And so this is a slightly tilted view of this above surface, which represents the contour map below the spheres. The numbering on the spheres corresponds in this case to the node positions in the MCTS tree, and these numbers roughly correspond to the order in which these candidates are being explored. What we have done is that the MCTS, which is typically so successful in discrete action space problems, we have made three important modifications to it. The first is to ensure that only unique leaves are actually explored during the MCTS. And this avoids the common issue of convergence of two initially separate MCTS branches converging to the same region of the continuous action space. More importantly, this solves the problem of multiple representation or degeneracy. So if you have degenerate solutions, which is what you typically encountered in several physical problems. So imagine that a face, a structure could be represented by varying unit cell definitions. And so we don't want actually the MCTS in the case of a structure search to actually lead to different structures that are just scaled up. The second concept provides a meaningful structure to the algorithm with the child leaf searching within a narrower region within what was searched with the parent node. The implementation of adaptive sampling of playouts allows us to improve the quality of the playouts, especially in a high dimensional search space, the random simulations are biased to sample regions that are closer to the parent leaf. And so with these kind of modifications, the MCTS was first tested on a variety of different so-called trial functions, functions for which we know the solution. So some of these functions are represented here. These are 50-dimensional functions, and we compare the performance of the MCTS to those of some other popular optimization techniques that are typically used. What we find is that in all of these cases, and these are fairly high-dimensional surfaces, the MCTS is able to reach a solution in fewer evaluations and have a solution quality that is better compared to some of these other techniques that we have actually compared it with. And of course, we applied it to the problem of parameter optimization. And what we were able to show is that for a variety of different elemental systems across the periodic table and over a sufficiently large energy range, most of the cases we were able to actually look at energy ranges that span 4 eV per atom. So not just near equilibrium, but also far from equilibrium. We were able to show that the errors that you get both in energies and forces were fairly low. And considering that this is a physical model, a Tursoff model that is actually being parameterized, these are actually quite low compared, considering that the models are computationally efficient. In addition, the MCTS is a derivative-free technique, and we applied it to the problem of using a neural network with thousands of weights, and we were able to show that this works pretty well even for optimizing weights of the neural network, as can be seen here in the parity plot that compares the model performance with respect to that of the reference DFT. For a couple of systems. So we were able to develop for several different models across the periodic table. And now what we are doing is expanding further. And one of the emerging trends in material science is and needs as well is to have explainable machine learning models. And so in this context, we are using symbolic regression to learn physical models that describe the interactions between the atoms in the system. So we are using an equation learner network, and our preliminary results on a model copper system look quite encouraging. As you can see, this is a traditional embedded atom model, which works very well in the near equilibrium region, but far from equilibrium is where it actually starts to struggle in capturing the energetics of those configurations. And so our symbolically learned model does not just well near equilibrium, but also far from equilibrium is able to capture the energetics as well as the dynamics of such configurations. And so these models are interpretable, and they capture not just near equilibrium, far from equilibrium at low computational costs. And this is low compared to state-of-the-art ML models, and these are physics-based models that we are actually learning. So we are aware that there is an effort on developing foundation models. Several of those, our next speaker is also developing foundation models. And the advantage of these is that you could study a broad range of materials chemistry and physics. There is an effort ongoing by several researchers. And so in this particular case, an equivariant graph tensor network was developed using a materials project, and this was found to be quite successful in describing diverse chemistries across a variety of different phases. We want to expand on that, include metastable phases, include nanoscale structures, and use that to actually develop foundation models that work well for nanoscale metals and alloys. So that is something that we are currently in pursuit of. And then I will quickly turn to the next thrust that we have, which is on AI-based inversion of multimodal data sets. And our focus is on a technique called as coherent diffraction imaging, which is a lensless technique that allows us to obtain full operando information of lattice dynamics in 3D. The challenge is that only the amplitude or intensities are recorded and not the phase. So applying a simple inverse Fourier transform to information with only intensities is insufficient to create an image from diffraction pattern due to the missing phase information. And this is the phase problem. And so in order to reconstruct and retrieve the real space information from reciprocal space, one needs to go through a tedious face retrieval procedure, which is obviously slow and precludes real-time information extraction and deployment. This problem is only compounded by the fact that there are going to be large volumes of data that are generated and going to be generated with the APS upgrade. So there's been a 10 to 100x increase in the data volumes over the last few years, and combined with the computing limits that we are all aware of, as well as the increased data resolution that will result from the upgrade. What we are looking at is typically like 1,000x more data that is going to be generated. And so in that context, we have, along with my colleagues, Matthew Cherukara at the Advanced Photon Source, introduced a 3D coherent diffraction imaging neural network, which is a deep convolutional neural network and differential programming framework trained to predict 3D structure and strain solely from inputs of 3D X-rays coherent scattering data. So these networks are designed to be physics aware in multiple aspects, in that the physics of the X-ray scattering is explicitly enforced in the training of the network, and the training data are drawn from atomistic simulations with models that are representative of the physics of the underlying material. So we further refine the neural network prediction through a physics-based optimization procedure to enable maximum accuracy at lowest computational cost. And so these 3D CDI neural network can invert a 3D coherent diffraction pattern to a real space structure and strain hundreds of times faster than the iterative phase retrieval procedure. While these deep learning models have been developed to either provide learned priors or completely replace phase retrieval, the model still requires vast amounts of labeled data, which can only be obtained through simulations or performing computationally prohibitive phase retrieval on experimental data sets. And so one of the latest advances building on that work is to, this framework called AutoPhase NN, which is a deep learning based approach which learns to solve the phase problem without the need for labeled data. So by incorporating the imaging physics through a forward X-ray scattering model into a deep learning model during training, the AutoPhase NN learns to invert the 3D Bragg coherent diffraction imaging data in a single shot without ever being shown real space images. And once trained, this AutoPhase NN can effectively be used in data inversion 100x faster than phase retrieval without while providing comparable imaging quality. And so we are extending that to now probe defects. And one of the problem with defects is that there is there's a need for large training data sets. And so in that context, my colleagues are developing workflows that take advantage of this continual learning, which essentially, in this particular case, the problem is identifying crystalline line defects in samples from raw coherent diffraction data. So this workflow combines coherent data generation with training and inference of deep neural network defect classifiers. So this is a continual learning approach where we generate training data as needed based on the accuracy of the defect classifier instead of generating all the data a priori. And so this is a smart continual learning approach where we have shown that you need 98% fewer training data based on this smart data generation on demand compared to traditional ways of actually training these networks. We are further extending that to other modalities, such as the X-ray photon correlation spectroscopy, which is typically used for studying soft matter dynamics in the mesoscale or microsecond timescales. And then we are also working with the Berkeley lab to actually not just develop the digital twins for spatiotemporal experiments, but also expand that to material synthesis and polymorph expansion, focusing both on the thermodynamic landscape as well as the kinetics. Can we learn time-dependent protocols for polymorph selection? So those are things that are underway. Our vision is to actually combine all of these different tools that are being developed to have a digital twin where users can actually explore the most interesting physics and chemistry in a virtual environment. This allows us to optimize the use of instrument time, improve user experience, and accelerate scientific discovery and design. So with that, I would like to thank you all and turn it on to the next speaker.
Can you guys see my screen? I would take it as yes.
Yes.
Yes. All right. So, hi, everyone. It's great to be here. I would like to thank the organizers for giving me the opportunity to talk in this webinar. My name is Kamal Chaudhary. I'm a staff scientist at NIST. Today, I'm going to talk about a very interesting topic called Atom GPT for inverse material design. This project is a part of a bigger infrastructure called Jarvis, Joint Automated Repository for Various Integrated Simulations, which is available at jarvis.nist.gov. So before I go into the details, let's talk about what is inverse material design. And I'm very glad that previous two speakers actually allude to that a little bit. So let me clarify a little bit more about this. So what is inverse material design? So in material science, usually we deal with structure property relationship, or in a better way, processing structure property performance relationship. But let's focus on structure property relationship. Now, when I say property, it might mean scalar properties like band gap of a material, superconducting transition temperature, so on, or a spectra such as X-ray diffraction, or an image like STM or STEM image, right? So these are properties. Now, when I say structure, it might mean atomic structure, microstructure, and so on. So what we want to do is establish a relationship. Now, in a forward material design, what we go through is a screening-based approach or a filter-based approach, like this is the candidate material and that is the fine-tuned material and so on. And that's how we discover or design new materials. What inverse material design tries to achieve is go directly from property to structure. Now, although this idea is very fancy, it's very challenging. Why? Because there is a huge combinatorial challenge in terms of periodic table elements, in terms of atomic structures, and so on. This is a huge task. So it's not that easy. There are certain methods available, such as genetic algorithm, Bayesian optimization, Monte Carlo, cluster expansion, but they can only handle only certain amount of complexity. Now, the idea of inverse design is not new. It was one of the first paper I saw is from Alex Zunger in Nature Chemistry in 2018. It's a very interesting paper, a good read. So based on this, we started thinking about this. In 2023, we published a paper on inverse material design of next generation superconductors using generative models. And this year, okay, let me move this. I published a paper on Atom GPT, and I'm going to discuss about this one. So hope the idea of what is inverse material design is clear to you. So now, when I do material design, inverse material design, there are certain things we need to be aware of. Number one, there is no unified physics-based model, at least to my knowledge, to do inverse material design. So one of the tools that we can use is the AI models. Now, when I say AI models, there are different types of AI models. Some are like feature-based machine learning or graph neural network or generative pre-trained transformer. So we're going to discuss about different type of models, different databases that will be used, and finally, most importantly, benchmarking. How do you know that this is state of the art, or how do you know this is reproducible, and so on? So these are the three components that we will discuss. Number one, database. Number two, benchmarking. And number three, AI models. So let's get into this. All right, so let's talk about database. So any machine learning task requires a huge database or certain amount of database. So in this work, we'll be using Jarvis infrastructure, which is available at jarvis.nist.gov. All right, let me move this. All right, so you can go to the Jarvis and you'll find databases, web apps, tools, tutorials, and outreach events there. You can sign in up for free. There is no charge for this. It was funded initially from Material Genome Initiative in 2011, and now it's funded from the U.S. CHIPS Act, which is one of the highest infrastructure probably in the history of United States. So again, the Jarvis is available at jarvis.nist.gov, established 2017. The idea is to use density functional theory, machine learning, force field, derived apps to design or optimize new materials. So again, I encourage you to check it out. Now, this is the website, and just an impact of this website, I can show you that it already established in 2017. We have published over 45 articles, over 4,000 citations, and we have about 150,000 users worldwide, which is not like Facebook or Google, which has like a few billion, but compared to material design community, I compare 150,000 is reasonable. And also in terms of materials, we have about 80,000 materials and millions of calculated properties. We have our data available in Figshare also, so where we saw about 1 million download of the code and data. Recently, Jarvis was highlighted in the NIST strategic plan for US CHIPS initiative as a computational metrology tool for standardizing the computation tool. So you can take a look on the strategic plan as well. So this is the brief success story of Jarvis or NIST.gov, and the second component, as I mentioned, is benchmarking. So now, when I say benchmarking, there's a difference between this and something called reproducible benchmarking. Every year, we see a lot of benchmarking paper, but I doubt how many of them are reproducible. So I would like to point out this paper in Nature, which says 1,500 scientists lift the lid on reproducibility. It was very surprising to see that only 0.5% to 30% max papers are reproducible. More than 75% or 70% papers are non-reproducible. So you want to have a platform that can enhance reproducibility, which can enhance transparency, which can decide what is validation, what is fidelity of the data set, and so on. So based on that idea, more than 5 national labs and several universities collaborated to develop this platform called Jarvis Leaderboard, which is available at this website. And the idea is to have a reproducible benchmarking for artificial intelligence, electronic structure, force field, quantum computation, and experimental tool set. And different benchmarking platforms are available for each of them. So there are about 9 million data points available in this Jarvis Leaderboard right now. When I say benchmarking, there are two aspects for benchmarking. Number one, contribution, and the second is benchmark. For which we can call a reference point. For experimental measurements, experiments are the benchmark. For quantum computation, analytical results are the benchmark. For force field, electronic structure is a benchmark. And similarly, for AI is a test data. For electronic structure is experimental data. So you can find more details about this benchmarking platform in the Jarvis Leaderboard paper. Each of the benchmark data must have a well-defined peer-reviewed associated DOI with it, so to be considered as a reference benchmark. So we talked about databases, and we talked about benchmarking. Now let's talk about the models that we're going to use. First one we're going to talk about is a graph neural network. Especially for atomic structure, if you look at this cute little picture here with blue spheres of silicon and red spheres as oxygen, so you can see that these can be considered as nodes, and these bonds can be considered the edges, which constitute a graph. So a graph is a collection of nodes and edges. Now you can distinguish the red atom from the blue atom from its atomic number, atomic electronegativity, and so on. You can have all the bonds, take a radial basis function, in a way histogram of all the bonds, and that way you can distinguish one material from other. And now this is fine until 2018, but and graph neural network was used successfully to predict properties. And then in 2021, we published an atomistic line graph neural network, which can capture not just the nodes and edges, but also angles using something called line graph. So a line graph can be considered as a graph of graph, where the edges are considered as nodes and edge pairs are considered as the new edges. So we found substantial improvement in performance using this line graph. I'll not go in details of this, but there are several publications in terms of align property predictor, a unified graph neural network force field for the entire periodic table. The idea is you can simulate or geometry optimization of any combination of periodic table elements in this align FF. We did for phonons, superconductor transition temperature, electron density of states, for carbon capture, and so on. So I'll not go in details of this, but you can check it out our GitHub page here at usnis.gov/align. So this is about align. We use this for inverse material design in the following way. So for a superconductor design task, so suppose the idea is you type a prompt such as generate me an image of a bear with a guitar, and this will generate you this image, right, in DALL-E. But the idea is can we use something similar for material science? So we use the CDVAE, back then crystal diffusion variation autoencoder model, which takes the graph, makes the hidden feature, and from the hidden feature predict the atomic composition and also the positions, and that can be used for denoising to predict the atomic structure. And I'll not go again in details of this. It's published in Journal of Physical Chemistry Letters that we actually computationally discovered several new superconductors using this technique with the help of CDVAE plus align. So this was very good. And then we moved to second model, generative model called GPT model. So at this point, I feel like most of us are familiar with what is ChatGPT, but when I started this project in about 1.5 years ago, I tried a simple prompt. This magnesium boride is a hexagonal material. Predict me the TC of this. So it did not work, at least at that time. So, and also more, so it's not very well suitable for material design tasks, especially. And ChatGPT also, its models are proprietary. It's hidden, so we don't know whether the model output will change from today or tomorrow, or maybe the same day the responses are changing. So it's very difficult to use this for something like scientific design task. So that was the motivation behind developing the Atom GPT, to integrate material science knowledge in GPT and make the models openly accessible. So the idea of Atom GPT, it can be used for both forward design and inverse design. So in forward design, you predict atomic structure to property, or in inverse design, you have property to structure. Now, these are the two prompts of the forward and inverse models. In a forward model, you have, for example, magnesium boride is this space group. This is the bond length. Predict me the TC. This is the forward model. Inverse model would be, so this is the formula. This is the TC. Generate with the atomic structure, description with lattice length, angles, and coordinates, and to generate to a string. So it's in other ways a string to string mapping in terms of inverse material design, if it makes sense. So let's go a little bit detail about what is this Atom GPT architecture. So it's based on the transformer architecture. Is again, which is based on this paper. It's called Attention is All You Need. It's one of the highest cited paper in the history I have seen, 140,000 citation in 7 years. And the idea is you take the text. So for example, you take a dictionary. There are 200,000 words in a dictionary. You can tokenize them, give the number 1, 2, 3, up to 200,000. And then you can, this token, you can take a text, tokenize it, and understand the relationship. For example, hi, how are you? You'll say, yes, I'm fine, something like this. You can try to establish the relationship within these tokens, and now you can decode it to get the message. So this is what is happening in the transformer architecture. And there are several transformer models which is available at, for example, Hugging Face library. One of the one which we use in Atom GP is called Mistral AI 7 billion model, which is a publicly available model. Now, this 7 billion parameter is a huge task to train them. So we did not train the entire 7 billion parameters. We use something smarter called PEFT, parameter efficient fine tuning, using low rank adaptation technique, where you freeze most of the parameter and vary only few 100,000 parameters. And also, instead of loading all your weights in 32-bit or 64-bit, you load them in 8-bit floating number, or even 1 or 2-bit floating numbers. So in this way, you save a lot of computational power. So using this model, I developed this Atom GPT Mistral TC SuperCon model, which is available in Hugging Face, and it has been already downloaded multiple times from several users, as you can see. And you can use this model to generate inverse design materials openly. So a little bit more details about this. So one of the techniques we, as I said, is use PEFT under LoRa, and also automatic mixed precision, where we try to load the weights instead of 16-bit to 4-bit or even 1-bit. And also a very interesting paper came out called ROFormer, so rotary position embedding. So in this one, we instead of finding the relationship between this token in a linear way, it tried to do some sort of rotation matrix, and it's a very efficient way of generating next tokens. So I'll not go in details of this. So you can find more details about this in the Atom GPT paper. And not just theory, you can actually try this today on Google Colab. You don't need to install any software. Just go to our GitHub page, and you can use this model to, for example, use a forward model, structure to property, or inverse models, property to structure. Also, you can use this on a Hugging Face interface. And it will be the model. We are still in the progress, but this model will be available in the Jarvis website as well. So we compared this model with for forward tasks for CGCNN and Align, the graph network model I previously talked about. And Atom GPT was quite comparable in terms of forward material design tasks. And especially for inverse material design tasks, we saw that it's much better than the diffusion model like CDVAE in terms of RMAC metric. So it was very promising, and it's much faster to train and much faster to predict. So it's super promising technique in my opinion. So as I said, all of this data is now available on the Jarvis Leaderboard benchmarking platform. So for example, here we are trying to compare the superconductor design task on the Jarvis Leaderboard Atom Gen DFT3D-TC SuperCon dataset. And you can see we have compared CDVAE and Atom GPT, and and if you have new models that you want to kind of add, you can feel free to do that following our guidelines here. So this is fine, and we did some after generating this materials using Atom GPT. We actually run a DFT calculation to predict whether some of these materials that are superconductors or not. So we found one of the newly discovered superconductor NB2B, and we found the TC to be 5 Kelvin, which is not like room temperature, of course, but it definitely is a good proof of concept that this kind of idea might work. Now, this is fine for scalar properties, but as I said earlier, that material property can be a scalar, a spectra, or image, and so on. So in this case, we are trying to use this Atom GPT for spectra, especially for diffraction pattern, which I call diffract GPT. So the idea is you take extra diffraction pattern, you use Atom GPT and generate the structure, you use align FF to kind of fine tune or optimize the crystal structure, and this is how you generate the full structure from extra diffraction. And this is, I just patented this about a couple of weeks ago. So the patent will be coming out. This technology will be patented by NIST in a couple of weeks. And I think these are revolutionary techniques in terms of inverse material design. So if you have any thoughts and suggestions to collaborate, feel free to reach out. There's a huge promise in this particular field. So finally, I would like to conclude this talk with a small 1-minute video, especially for the audience who are not expert here. So let me play this video for a minute. So finally, I conclude this talk by highlighting this NIST Jarvis database, Jarvis leaderboard benchmarking platform, Atom GPT model, and also I would like to highlight our upcoming events at NIST called Artificial Intelligence for Material Science Workshop, Quantum Matters for Material Science Workshop, and ReproHack, Reproducibility Hackathon. You can find details about this in the jarvis.nist.gov outreach tab. And also, if you are a US citizen and would like to work with us, feel free to reach out as a postdoc and we'll be happy to work with you on that topic. So these are some of the social media links. I'm available on LinkedIn. I have a YouTube channel also. Feel free to check it out. This is my GitHub ID and this is my email. Feel free to let me know if you have any questions. So thank you again for your attention. And I would like to thank again all the organizers for inviting me for this talk.
Right. Thank you, Kamal. I'm Elizabeth Mansfield from NIST. I will be leading us through the question and answer. First, I'd like to thank all of the speakers. I think you showed a great range of resources out there, so thank you for that. Also like to thank Matt and Noor from NNCO for helping to organize this workshop. And we will jump into questions. If you have questions, please put them in the chat. But we'll start with one generic question, and that is, how does somebody collaborate with you to access these resources that you have shared with us today? Do you want to start, Kamal?
Sure. Yeah, I can start with that. So it's a great question, how to collaborate. One of the ways I find to collaborate is have a common problem to solve. And this problem solving strategy is a great thing to start with. So feel free to reach out. I showed you different things, at least from my presentation. And if you find something common you want to expand on, we are very happy to collaborate on that perspective. Again, I would like to hear from others as well.
Yeah, so I am at the Center for Nanoscale Materials, which is a user facility. So there is a procedure to access all of the resources, including the tools and softwares that was discussed through a user proposal system. And that is open to users all across US as well as international users worldwide. You could go through so there is a 2-page proposal. As long as the topic is nanoscience, you could look at the variety of software tools as well as other tools that are available at the center and apply for it. I can share the link on how to actually go about. So you register as a user and then you submit a user proposal. The user proposal gets reviewed, and almost like 70-80% of the proposals are allocated time, and that is one way. The other way is, of course, to just write directly to us to collaborate, and we will suggest you the same thing, that you have to go through the user proposal system. So that's one way of actually engaging, and we are looking forward to having a diverse user base. So please feel free to reach out.
Same answer for me. Please feel free to email me. It's very easy to just search for my name and find my website and contact information. And I used to be part of a user facility at a DOE lab. Any of the 5 NSRCs, the Nanoscale Research Science Centers, you can just search to find which one is closest to you. And any of the staff there, including all my former colleagues and everybody there, would be more than happy to discuss research projects. And as mentioned, it's just scientific interest, access to the people, to the tools, to the experiments. It's all free. It's a totally amazing opportunity for researchers. And in particular, at the Molecular Foundry, they really try to serve industry users too, right? So even outside of sort of core academia, I would encourage you to reach out to the appropriate scientist.
Great, thank you. We have a question in the chat that came in, I think, during Kamal's talk. Can we apply the same AI methods to develop a fluorescent material rather than superconducting?
Yes, so the model is agnostic to what kind of property you're trying to train. So yes, the short answer is yes. And if you have any technical difficulties to setting it up, please feel free to raise a GitHub issues or send me an email. I'm very active with email, so feel free to reach it out. Yeah.
Great, thank you. And I think this is a general question, so whoever wants to jump in. What are the practical limitations of data management or curation infrastructure and the implications of generating terabytes of data over the course of a measurement? Also, are there post-acquisition steps that need to be taken to clean or pre-process the data from different sources or streams before being fed into different models?
Well, maybe I'll tackle that one first. So it is actually a huge challenge. And in the Department of Energy, we have not sort of settled on a solution for this. There are large-scale hosting solutions. I think Figshare was mentioned. There's the Materials Data Facility, of course, Zenodo out of Europe. There are ways to sort of store it. But a huge problem that we have is a lot of the raw data that we record, we actually don't want to keep. We want to distill it down to the information stored inside, right? To the valuable part of it. And so that's where pre-processing is incredibly important. We try to boil the data down, compress it, bin it, extract what we need to out of it, and then not store it long term. And current detectors are recording terabytes a second. Current simulation methods are recording or simulating terabytes of data, like DFT, for example, in hours for every single material. And same thing with these ML databases, right? So what I think we should do, I should call out the DOE a little bit and say, and other institutions here in America, we should look to Europe, right? NOMAD and other similar gigantic efforts to sort of centralize this infrastructure is the key to solving it and making it sort of accessible to everybody here. I can't be more specific about the pre-processing and cleaning steps because it depends on the experiment. Are you doing coherent, diffraction? Are you doing 4D STEM? Are you doing ML traversal of some simulated model? You have to email us to ask for more specifics, I think, for a specific question.
Yeah,
I think MDF was mentioned. Sorry, I can go ahead. MDF was mentioned from NIST. So NIST also has NIST materials data and other resources. I have seen few terabytes here, but a terabyte a second sounds like a lot. So I'm not sure about
a couple hundred gigabytes there, but nothing more so far.
Yes, and not more than that. Yeah.
Yeah, I mean, so this is a well-known problem of the need for data infrastructure, especially at the nano centers where there is a heterogeneous data set that is generated. Like, you know, you have microscopy, spectroscopy, you have, you know, the X-ray nanoprobe, you have synthetic data being generated. So being able to handle that is a challenge. And there are ways in which some of our staff are actually proposing to develop a joint data infrastructure. So my colleague Maria Chan is actually interested in developing such an infrastructure that allows users to pre-process. Again, it depends, as Colin said, on what specific tasks and instrument you are interested in, where's the source of data and so on. But there is a need, and it is an unsolved problem. There are also some other challenges with being able to access user data and so on. So it's more complicated than what it looks like. So so some of those things are being resolved at different levels of DOE leadership as we speak, and hopefully we will soon have a solution that is like Europe has all these different data infrastructures. I guess we can also develop some of those without too much hassle. So that's the hope.
Yeah, that's great. Thank you. For Colin, there's a question. You said you have to select areas for identification of the diffraction pattern during the processing step. Is there a certain ambiguity on selecting the areas of the diffraction data?
Yeah, the answer is yes. When we're dealing with noisy characterization data like this, there's always the problem of thresholding, of saying, okay, when are we going to set our thresholds too low and get false positives in the data, or set our thresholds too high and miss some of the information, right? And this is actually areas where machine learning can really help, right? The sort of conventional or classic computer vision and image processing methods are actually significantly less robust than modern machine learning methods here. So one of the going forward research thrusts of my new group here is to really focus on taking these conventional image processing and diffraction processing routines where there might be human in the loop steps, right? Like selecting a specific area and completely removing the human from the loop, and using ML, both supervised and unsupervised and even self-supervised now, approaches that are going to give you not just a more reliable answer, but with very high probability be reproducible. I think in some sense that's even more important, right? And I think one of the speakers mentioned understanding ML, right? Like interpretable ML, right? That's also very important when you go down through the chain of custody of the data from the measurement to the pre-processing to the processing to the analysis to the outputs, right? We need to be able to sort of track down where errors or where ambiguities come from, and then work to remove them. So that was a little bit of a wide answer, but absolutely ML is can't do everything, and it is overhyped, but this is a task that it's very, very well suited for.
Yeah, I really enjoy all of you talking about reproducibility, calibration throughout your talks. That's really great. We'll go to the next question in the chat. I think this is for Kamal. Are you using MGI and ICMSE to refine material discovery through Atom GPT, or is Atom GPT improving ICMSE?
Great question. So
And can
I
you
would
remind
see-
people of those acronyms?
So MGI is Materials Genome Initiative. ICM is Integrated Computational Materials Engineering or something like this. Please, I know it's being recorded, but anyhow, sometimes I forget its acronyms. But the idea is basically accelerated material design, right? So it is along the same lines of accelerated material design, but this is like super acceleration. Instead of going through databases, looking out what's going on, filter out and stuff, we directly just give like what Google versus ChatGPT, right? You Google, you go to the search, you find your search link, click this, go there. Instead of ChatGPT, you just write a prompt and you have the entire structure. So in a way, aligning with ICME and MGI, but several times faster and efficient, in my opinion. So hope that answers the question for the user. But this is a good question, I think.
Okay, thank you. We have another one for you. So if you just want to keep going. For your presentation, they envision applications in microradiation detection and dosimetry. Care to elaborate on how you envision radiation interaction into synthetic fluorescent materials?
Envision radiation interaction into synthetic fluorescent. So I have not worked with fluorescent material before, but I feel like it should be at least easy to set up this problem if you have the database. First and foremost, the important part is a well-curated data set. If you have a well-curated, diverse data set, I can almost guarantee you that 50% of the problem you have solved there already. So if you have the data set, which is diverse and well-curated, you can use ATN-GPT, GNN models, or any other models, and you can compare them, which one is more suitable for your task, right? So again, that would I would start envision that first get the data set from ourselves or from other databases like Figshare or Zenodo or Nomad or any other databases like this. And if you don't have it, really, I would encourage that have infrastructure to generate them, because I personally have seen that people who work in machine learning, for material science at least, they tend to develop their own data set to kind of step into the field. So if you really want to have a significant impact of this and have a full control on your model and data, I would recommend that having your own data set on this fluorescent and also benchmark with existing data set with experimental data. And once you have done that step, then you can use ATN-GPT or any other model like this to have a material design task. So hopefully that clarifies the question.
Thank you.
If I
Nil,
can
did you
jump
have
in?
questions?
Yeah, so I have again, thank you, excellent presentations. We enjoyed all the three. Colin, I have a question about the electron microscopy image analysis, the three-dimensional. One of the challenges we have, our scales are different. We are looking at biological material, cells and tissues, and you're looking at really narrow, and then you describe the challenges to go from small scale to, in a micron, and then to get into the 3D. One of the challenges is the software. So we buy some software, we learn the software, and we use it. The next generation software comes in from a different vendor. The question to you is, since you're using software to analyze all the data, is that software publicly available?
Yeah, so I'm also working on biology too. So with Henning Stolberg's lab at EPFL, we just published in Nature Communications using our 4D STEM methods, tychography and parallax in particular, to do structural biology to solve proteins, right? And actually, that's not even the strength of STEM. We're sort of closing in on TEM, the conventional way biologists use to do structural biology, but we're not past them yet. The real power of STEM is very, very thick specimens. So in cryo electron tomography, you rotate your volume, and it's probably going to be impossible to go to like a human cell or plant cell, but a bacteria is 1,000 nanometers sort of scale. And we do think that we can push to thicknesses that large using our approaches and our software. And so to answer the question at the end is, all of our software is open source. It's all free to use. And that's sort of where most groups start. I think all groups need to go to do the next step, which we've done. All of our data sets are publicly available. We write tutorials on each of our methods. We have them in Colab. We have them on GitHub. We have them, teaching around the world at workshops. We taught a Pi-40 STEM workshop at MRS this last conference, for example, and several more of these upcoming. So I would encourage folks, kind of following along with what Kamal was saying, right? If you want your data to be useful to the community, you have to annotate it, you have to make it really complete, you have to make it publicly available, freely available, and you should even include code for how to interact with it, how to pull information out of it, right? That's what we try to do with all of our software. And so, to tie it home, Anil, this is why the biologist group was able to work with us, right? They use a software called CryoSpark or rely on to do their structural biology, but they couldn't go from the microscope raw data to the inputs of this software, right? But Pi-40 STEM, because it's so well documented, so many examples, so many tutorials, etc., with very little help, they were able to adapt our reconstruction software to their pipeline, and it resulted in a successful publication. So I think that especially in computational science, we have the edge because we're used to working with tools like GitHub and these databases, right? but I would like to see all scientific research go in this direction.
That's awesome, especially if they're publicly available and freely available.
That's important too.
Yeah, that's important because we spend a lot of money on software. Sometimes we don't have every year. Elizabeth, back to you. Are there any questions?
Can I ask a question?
Yeah, please go ahead. Come on.
Please.
Yeah, please, to the other panel members.
Yeah, I mean, I think I'm allowed to ask questions. So
Yes, please.
I liked both of the talks. I learned a lot. So I have a question especially to Colin. I think you mentioned you took the 4D stem and tried to predict the lattice parameters or something like this. How accurate was this?
Yeah, so I actually, I don't think I actually talked about it in this presentation, but we just have a paper that came out in Physical Review Materials, where we take raw diffraction patterns and try and predict the 3D crystal family and space group and then lattice constant. And the answer is it's a sliding scale, right? So we used random forest networks, which I think is just not the right tool for this, but we did release 360 million diffraction patterns publicly, and we're working on annotating and hosting the data so that other groups, experts like yourself, who are much better at machine learning than we are, could take the data and maybe solve domain problems. So how accurate was it? Mixed, right? Crystal and hexagonal, remarkably accurate, right? I mean, there are ambiguities you can't get around in 2 dimensions versus 3 dimensions. If I take a cube and I stretch it along the beam direction, it becomes, you know, say orthorhombic or tetragonal, and you can't tell the difference. That's an ambiguity you can never defeat, right? But with a little bit of tilting, a little bit of 3D information, you can overcome it, as we showed. The other crystal systems, though, monoclinic, orthorhombic, etc., accuracy goes down with symmetries, right? And triclinic, we didn't even try. Like, the results were so abysmal that we just gave up on it. But given cubic materials, given hexagonal, it was actually remarkably accurate at predicting the lattice constant. And I think that if people who are better at machine learning than we are take a crack at it, they could probably do better still, right? So I would love to chat more about this with you in the future. The data is available, and we'll have tutorials soon for how to download and train on it.
That's really wonderful. Thank you.
Yeah, we don't see any questions in the Q&A window. I have another question, a generic question. Maybe feel free to jump in, any of you. One of the challenges for nanomaterial analysis, these are particle analysis, is the surfaces of these particles. And, you know, some of the irreproducibility comes from the coatings, especially when it comes to biological applications, a lack of coatings, inhomogeneity, heterogeneity of the coatings. Think of a particle. I saw the lattices of some nanoparticles there in the presentations with an organic coating, right? There are not many methods to look at the coatings, the inhomogeneity, heterogeneity in the coatings. Any of the things that you are developing tools, are they applicable to this domain? You know, one specific example is there were hundreds of publications on targeted drug delivery. So you have a particle, you have some coating, you have some antibodies targeting ligand. Proof of principle, excellent. Clinical translation, very minimal. And that is a challenge with that. So at that level, do you have any tools that can kind of answer those kinds of questions?
Well, maybe I'll take a quick crack at answering this. I would say we have 2 tools that are sort of potentially good at answering this. So one of the things my group does is atomic electron tomography, where we solve all the atoms of the material. Now, the challenge, though, is the accuracy is about 99%, but that's averaged over the particle. As you point out, it's the surfaces that are so challenging, and that's where atoms can diffuse, they can move, you have a biological structural unit, can be damaged by the beam, etc. There's just so many challenges in surface characterization. So here at Stanford, we just bought a microscope, though, that does the STEM, scanning transmission electron microscopy, but also pulls the secondary electrons off at the same time. And so it's my belief that doing secondary electron microscopy at atomic or near atomic resolution, that's the key to answering questions like this, because the sensitivity to the surface is extreme. The escape probability for a secondary is such that a surface atom or a subsurface atom can emit a secondary and it can escape, but you go 3, 4, 5 atomic layers deep, you get essentially no signal. And so you get the bulk signal from the methods we use now, plus this new secondary signal. And so I do actually think that that's probably going to be the way that a lot of these things are going to be characterized here. And there was a second technique I was thinking of, but it dropped out of my mind while I was thinking about secondaries. So maybe I'll let Kamal or Subrahmanyan take a crack while I think about the other one.
I mean, so
Subrah.
depends on what technique. So in our case, especially if you're looking at things like ligand distribution on the surface, synthetically, like we could actually have these coarser grain models that can actually capture and the dynamics of it, how they evolve and so on. The task then is to actually go ahead and either get the reciprocal space from processing of these molecular dynamics trajectories. And that is something that is doable for variety of different modalities. I'd say most modalities you can actually kind of get a complementary synthetic information. The next task is, of course, you have better control over the synthetic data, and how do you actually now translate this information that you are obtaining synthetically over a variety of different cases and have the correct interpretation from the experimental one where there are all these surface modifications. And that, of course, is technique dependent and also dependent on what is the quality of the synthetic data that you are able to generate and train the model. So at various levels. But there are similar problems. The defect identification problem is a similar one. Like how do you actually understand the distribution of different types of defects that are actually present? And so the surface is like one specific case of like, of that. And so can it be doable? Yes, if the price is right.
All right, thank you. In the interest of time, I want to just, on behalf of Anil and I, say thank you to the speakers again. I think this is a really great webinar series and a great introduction to these topics. So thanks again, and we'll see you next time at the next nanometrology webinar.
Thank you.
Right. Thanks.
Bye.
Bye.